Welcome to LLMs as Operating System course by Simplilearn. As AI systems grow more powerful, LLMs are evolving from simple chatbots to central platforms that can manage tools, memory, and intelligent agents, much like an operating system. Learning how LLMs function as control centers opens the door to building smarter, long-running applications that can plan, adapt, and remember. This new approach is transforming how we think about software, and those who understand it will be the forefront of the AI-powered future. By end of this course, you will be able to understand what LLMS is, what are the types of memories used, agent architecture, and also you will be able to build your own agentic system. So let's get started. So first let us start and know the basics and the advanced level of LLMS. So what is LLMS? LLMS stands for Large Language Models, which are powerful programs like ChatGPT that understand and generate human language. They can answer questions, chat, write stories, translate, and summarize, all by predicting the next word based on a prior text. So there are a few techniques that are used of how to achieve this. We'll come on to that later. For now, let's see some of the real-world example of LLMs. So firstly, we have ChatGPT by OpenAI, which is known for conversational brilliance. Then we have Claude by Anthropia, stands out for reasoning abilities. And then we have Google's Gemini, is all about advanced language insights. These showcase the wide applicability and transformative power of LLMs. Let's learn how our LLM is trained. So a large language model is built using a transformer neural network which was inspired by a real human networking system in our brain, which was introduced by Google in 2017. It uses self-attention to focus on important words in any position. LLMs are trained on trillions of words, books, websites, and articles. Training an LLMS is like teaching a child the rules of language, but not an extraordinary scale. Through this training, they grasp grammar, reasoning, factual knowledge, and even general world understanding. Imagine a student reading millions of books and synthesizing all the knowledge to answer questions or generate ideas. That's what happens during LLM training. It's what gives them the ability to speak and reason with such fluency. While LLMs are extraordinary, they have limitation. Their context window restricts how much they can remember at once, and they do not retain memory unless explicitly designed to. And even they hallucinate by producing false information. Additionally, biases from training data can surface in their outputs. Now let's learn about the memory of LLMs. Memory is essential for coherent interactions. Without it, every message starts anew, devoid of context. LLMs needs memory to stimulate long-term recall, hold relevant facts, and tailor their intelligence to user goals. It's secret ingredient for making AI feel like a human. Let's move on with what are the types of memory in LLMs. So there are two types where you can distinguish. One is based on ownership and the second one will be based on duration. So for based on ownership or scope, memory in LLMs can be categorized by ownership or scope, showing who uses the memory and how. For instance, we have conversational memory, which keeps track of ongoing chats, helping both you and the bot maintain continually. Then we have personalized memory, which remembers user-specific details like names, preferences, and making interaction more tailored. Then we have shared memory, which acts as a collaborative space shared by multiple users or agents like a shared project file. Agent memory reflects what AI knows about itself, such as its role and purposes. Lastly, we have task memory, which tracks steps during a specific task, ensuring smooth goal compilation. Next, based on duration or functionality, majorly it is divided into short-term memory, long-term memory, and editable memory. So let's get inside the short-term memory. Short-term memory in LLMs refers to temporary context visibility during the current conversation. Think of it like a chat bubble. It's limited by the model's context window, which may range from 8K to 128K tokens. Once the bubble is full, older messages drop off, making room for newer inputs. While short-term memory enables quick and responsive interaction, it's inherently ephemeral, disappearing as soon as the chat ends. Next, we have long-term memory. Long-term memory in LLMs takes the concept of recall to the next level. Using external storage like databases, vector stores, or memory APIs, it stimulates human-like remembering across sessions. Long-term memory allows continuity such as recalling your name or preferences days, weeks, or even months later. It's foundation for building persistent, personalized, and context-aware agents capable of truly engaging long-term relationships. Next, we have editable memory. Editable memory enables users to develop, to add, update, or delete stored information in LLM's memory. This makes interaction more dynamic and accurate by allowing corrections, updates, and removal of sensitive or outdated data. Editable memory is critical for correcting the mistakes in what the LLM remembers. Then we have updating facts such as changing someone's name or location. Then we have forgetting sensitive data to improve users' trust. This ability allows LLM agents to remain adaptive, avoid overload, and deliver personalized experience aligned with real-world needs. Now let's see why editable memory matters. Firstly, it improves user trust and control. And then we have enables more personalized long-term agents. And then we have prevents memory overload and confusions. It is critical for real-world applications such as AI tutors, assistants, and copilots. Let's see how chatbots to anonymous agents transformation happen. So chatbots are reactive. They respond to comments, back deeper understanding. Autonomous agents, on the other hand, are proactive. They use short-term and long-term memory to complete multi-step tasks and achieve goal dependently. For example, a chatbot might tell you the weather while the agent might offer you to reschedule your outdoor meeting due to the rain. This leap from static response to dynamic reasoning, defining the shift from chatbots to true intelligent agents. So here there is few of the differentiate of how chatbots will respond versus how agents will respond. Let's move on with the agentic loop. So agents operates through a structured cycle known as the agentic loop, where the first step is to plan, which is determine what needs to be done. And next we have observe, which is check the result of actions. And the third one is to act, which is execute steps such as using tools or querying APIs. Then lastly, we have learn, update memory, or refine the process if needed. This loop allows agents to continually improve, making them highly adaptive and capable of solving complex problems. Next, we have reactive versus proactive system. Now, reactive systems wait for instruction, responding only when asked. In contrast, proactive systems anticipate user needs and act independently and rely on memory for last context. For example, a reactive system might schedule a meeting when prompted, while a proactive system suggests the times based on everyone's availability. This evolution enables proactive agents to function more like collaborators rather than tools. Now let's get into self-editing, memory, and implementation. Now self-editing enables agents to refine their knowledge dynamically. It's not about just storing information, it's about revisiting outdated or incorrect data and deleting what's no longer irrelevant. Then this feature essentially for long-term agents such as assistants or customer services bot, which needs to keep up their memory organized and accurate. By self-editing, agents avoid clutter and contradictions, ensuring they remain effective over time. Let's see some of the importance of self-editing long agents. Imagine a AI personal assistant, research agent, or customer service bot interacting with your over a long period. Without self-editing memory, their stored information would become outdated, cluttered, and prone to errors. Self-editing allows these agents to dynamically revise their memory, clean up inaccuracies, and adapt new realities. This is capable of vital for ensuring long-running agents remain accurate, efficient, and trustworthy over time. For example, if a user moves to another city, the agent detects this change and updates the memory seamlessly. Next, we'll see how LLMs can modify their own memory. Self-editing empowers LLMs to revise stored data during or after conversation. Here's how the process works. The first step is to detect. The LLM identifies what needs to be changed, such as a user moving to a new city. Then we have step 2, which is to decide. Using reasoning, it determines what to update. For instance, replace the old address with a new one. And third step being write. The LLM rewrites or replaces the relevant memory part, ensuring the update information is accurate and usable. These steps ensure adaptive learning while maintaining consistency and relevance in interaction. So, what are some of the challenges in early implementations? Implementations of self-editing memory brought about significant challenges followed by innovative solutions to address them. So, one of the hurdles being trust issues. Users were cautious about giving LLMs the ability to modify their memory, fearing unintended consequences or loss of control. The second being accuracy versus over-editing. Striking a balance was difficult. Over-editing could erase relevant data, while under-editing risked leaving outdated or incorrect information untouched. Next, we have change tracking problems. Early systems lacked mechanisms to properly track what was being updated, making it hard to ensure consistency in memory revisions. Now, what are the few solutions for these? Firstly is building the trust mechanism. By introducing transparency like memory logs or edit histories, user could see what changes were made and by forecasting confidence, which is memory versioning. Next, we have validating layers. Add pre-edit. Validation checks helped ensure memory updates were accurate and aligned with agent's goal. Nextly, we have version control system, which is robust version controls allow agents to track edits, revert changes, and maintain accountability for memory modifications. These innovations laid the groundwork for effective self-editing memory in long-running AI agents, ensuring adaptability while maintaining user trust. So let's create a chatbot with a editable memory feature and see how this works. So for any chatbot, we should import few things. So we'll start with OpenAI. So let's import OpenAI from a local module. This will be connecting to OpenAI server. So we have from helper as the server. Next, I will also import OpenAI class from the OpenAI package. So here we have. And also I'll import JSON, which is a must and should for any chatbots. Now let's call the OpenAI key function. This will allow to connect to the OpenAI securely. After this, we should create a client object which can communicate with the OpenAI's module using the API key. So let's create the client. So we have client is equal to OpenAI. Now this is done. Now let us set what module we are going to use, like what module of ChatGPT or OpenAI's. I'm going to use GPT's 4.0 mini version. So the model will be equal to GPT. You can just Google what is the. And then now let's create a memory box which is creating a dictionary with two types, which is human and an agent, both starting empty. Firstly, I'll just run this, and there is a error, and the error here should be open AI, so this I should be in capital. Let's see now, and yeah, we are good. So coming back, we are creating a memory box with two keys, which is human and agent. Both will give it, for now, let's initialize it as empty. Human is 1, and then the second one will be next. Let me give a base system prompt. Okay, so we're giving a system prompt. It should be system. You can give whatever information that you need your system to keep it in the mind for the entire conversation. You can just close it. Now, since the system prompt is ready, we need a way to actually update the chatbot's memory while chatting. This is conversational memory, if you remember. And let's define a function that can add a piece of text to a specific section in the agent memory. First, let me just run it, and it's good to go. So we have, let's give core memory. You can give your names. Then for this, let's give agent memory. So let's run this to make sure there are no errors, and there are no errors. Now here comes the part where you should tell the bot how to use the memory too. So coming with core memory, and save. Let's give type and function also. What else we can give? We can give description also. So description. Let's give another description. Okay, sorry. Put it in double quotes, descriptions. So the second description, I'm keeping it as must be either human or an agent. Must be either human or an agent. Let's say memory to save in this section. After this, let's close this. Be careful with the parenthesis, because you might not really know which parenthesis you're closing. And section. Let's check for any errors. There is errors. There is so in 14th line there is an error. So let's check for that. So here there is repeated double quotes. So just let's put it in line 6. So let's just check. Okay, so there is a spelling error here. So I have missed N here and N here, it's function. And now let's run it. There is still the same error anywhere else. Let's quickly just check if there is any other error. Okay, there's a semicolon missing, and let's run it now. So here it is showing the error, so let's check. So this sentence is fine, and okay, I've added a full stop extra. Let's remove that and now run it. There is another error which is in the same line here. Okay, so here there is a comma missing. This is the 9th line. It's okay if you are getting errors, just rectify them because there will be very small errors. So here I have not given a comma, so let's give that and run it again, and we are good to go. Now since the memory is there, now we have to improve the agent's decision making. Like something important is said, the bot might call the core memory, save the tool automatically instead. So for that, let me give system prompt OS, which I'll be assigning it to the existing system prompt. Plus I'll give another description which will be the condition will be you must or write after this. Okay, and we are good to go. Next, let's define a function agent step that takes the user message and hands a complete round of interaction. So an entire definition should be done, function should be built. So we have, let me give the function as agent step user message. For this is for user messages. Firstly, role system should be given, then content. Okay, let's end it here, and then system OS, role system, and then give system. Next, you can also give the memory to it. So it will start with role system. Let's add it up with so that there is no complications here. User content. Let's close it up. So let's check for any errors. Okay, so now let's run it. We are good to go. Next, we need to start a while loop to call a tool and generate the user reply. So let's give while, and now we should send a message and the tool to the model and wait for the response. So for that, I'm giving chat completion, chat dot completion dot create. Let's give messages. So at last we can just close it up. We need to return a message from the model as a reply. This should be here. So here I've just missed the braces. So let's get back and close it. And as I told, we need to return the message. So we have dot message dot tool calls message dot content. Next, if the model decided to say something, then we need to extract the arguments and run the tool. So we have else. The arguments will be according to JSON so that we don't get any syntax error. JSON dot loads response dot message and also dot function and then core memory. After saving the memory, we need confirmation. So let's see how to give the confirmation. For confirmation, we just can append the messages. So we have messages, also tool, ID. Not tools, so let's call the function. So let's run this and see if there are any errors. And there are errors. Okay, this should be top. Okay, now let's just run. There is no reference, so I'm adding the reference of response. So I think now it should work. So now just let's run it, and still we are getting an error saying return is outside the function. Now I've put the return function inside the loop. So yeah, now we are good to go. So let's start with executing this program now. So let's execute. So we have usual way of executing with the main function. I think all the Python people who know Python will know the statements. Now let's give a welcome statement for initial starter. So we have print, and what's the message? Chatbot is started. And then let's give a warning, which if you type exit, you will be out of the loop. Okay, so I have to give single colon since it is a print statement. Exit and close it up. Now let's give a loop for continuous conversation, which is while loop, which should be running. And then we need a prompt to take the response from the user, right? So let's put user input. What should be the user input? Is equal to input. Initially you can just type when you see this U, and let's give a space. Next, if the user has entered exit, we should break out from the loop. So for that we'll create another if loop. So if user input dot lower exit, if the user by mistakenly puts an exit, then we need a break off from that. And we need to send the user message to the bot and reply in the store in responses. So let's keep response is equal to agent. We're calling the function step, agent step, and giving the user input. Now let's just print the chatbot's reply which we have got from the other side. So we have print. So you go to which format? Like bot, and here like this, and response. Yeah, this is the output. So let's see if there are any errors. Yes, there is an error. So let's just check. Valid syntax. There's a syntax error here. So I think there are no more errors. So let's run it and you can see the output. You can enter the message and here you can see a message of chatbot with memory is started and you can give exit. So let's give it an input of my favorite color is blue. Let's see what it does. There is an error, so let's resolve it. So here's the error. So the while loop should have been under the agent step. So since we have cleared that, let's run the cells. So this is done and run it and run it. So here again, now I can see my favorite color is blue. Now it should probably give us a response of got it, your favorite color is blue, and if there is anything else you want to fix here, so you can just write my name is Sheila and it will update in the memory. It is replying, nice to meet you Sheila, how can I assist you today? So this was a small example of how you can modify your memory, which is editable memory. Now let's get into MemGPT. Now what is MemGPT? MemGPT is a cutting-edge research project addressing the limitation of context window in LLMs. Inspired by operating system, MemGPT enables models to store, retrieve, update, and even forget information dynamically. This structured memory management lays the foundation for building smarter, long-term AI agents capable of handling complex tasks and interactions seamlessly. So what is a OS-inspired memory management? So MemGPT handles memory much like a computer's operating system, which includes core memory and archival memory. So core memory, similar to RAM, it offers faster access storage for immediate tasks during active uses. Whereas archival memory is compared to a hard drive, it stores long-term information that's less frequently accessed. By dividing memory this way, MemGPT ensures efficient data retrieval while maintaining organized long-term storage. Next, what are some types of memory in MemGPT? MemGPT's memory hierarchy mimics computer systems using core memory and archival. So one core memory, we already know it's a fast access and frequently updated for active conversation. And then we have archival memory, which is slower, large-scale storage used for long-term knowledge. This design balances speed and persistence, ensuring MemGPT remains efficient during complex tasks. So let's see memory flow and hierarchy of the same. So the memory system in MemGPT operates the cycle of think, use, store, and forget. So the information from the archival memory, which is a long-term storage, to core memory, which is active use when needed. After use, the data is either updated and saved back or discarded if irrelevant. This efficient process keeps the system focused and prevents unnecessary memory clutter. Next, we have function calls for memory operation. In MemGPT manages a memory through specific function calls enabling intelligent data handling, which includes insert memory, which saves new information into storage, and we have search memory, which retrieves past knowledge for use during the task, and then we have update memory, which revises stored data to ensure accuracy. And lastly, we have delete memory, which removes outdated or irrelevant information. These operations allow MemGPT to maintain an intentional and organized memory system. Now let us know what Letta framework is. Letta framework simplifies building memory-enabled LLM agents with system prompts, memory models, and tool integration. Letta allows developers to craft highly intelligent and responsive agents, whether managing tasks or personalized interaction. Letta helps create adaptive AI systems for real-world application. Let us see what are the components of agent in Letta. Letta agents are constructed using three essential components, which is system prompts, tools, and memory modules. So in system prompt defines the agent personality, behavior, and the goal. And in tools equip the agent with functional capabilities like search and data updates. In our memory modules, we have stored and retrieve critical information, allowing the agent to adapt and learn. These components work together seamlessly, forming the foundation for versatile intelligent agents. Now, how to create an agent from scratch? Letta offers a step-by-step approach to creating agents. First one being define system prompts, which is to shape the agent's personality and objective. Second one is to attach tools and memory modules, which is to equip the agents with functional capabilities. Then we have test and refine response using Letta's interface. Then we have set memory loose, which is customizing what to save, update, or forget. This process ensuring the creation of adaptive agents ready to perform complex tasks. Now, how does the interaction with the agents happen? Letta provides an intuitive interface for seamless interaction with your agent. Here's what it offers. Firstly, we have chatting with your agent. Test how the agent responds to various prompts and observe its behavior in real time. Then we have tool calls and memory logs, which monitors the tools the agent uses and check how memory is being inserted or updated during the conversation. Then we have adapting over time, which is watch as the agent learns and adjusts its memory dynamically, refining its performance for further tasks. This interactive approach helps developers evaluate and fine-tune their agents, ensuring they behave as expected and deliver meaningful results. Now, how is the managing of memory in Letta? We have memory management in Letta is flexible and developer-friendly, which includes customizable memory rules, which is define what the agent remembers, how long it persists, and when outdated information should be updated or removed. Then we have focus on the relevance. By fine-tuning memory parameters, agents remain sharp, responsive, and effective. Then we have multiple memory types, which is from temporary chat memory to persistent long-term memory. Letta offers solution tailored to every need. This versatility ensures agents are both effective in the moment and reliable over the time. Let's see some of the memory in Letta. What are the types? So Letta allows developers to define when to use each type depending on what agent needs to remember. So majorly there are two kinds, one being the chat memory, which is temporary memory used only during the current conversation, which vanishes afterwards. Then we have persistent memory, which is a long-term memory saved across sessions, helps the agent to remember important information. Let's see how programming agent memory, which is programming agent memory involves defining custom behavior to manage the information an agent remembers, updates, and forgets over time. Here's how it works. The first thing is remembering key user inputs. Agents can store important user details like preferences or frequently asked queries to enhance personalization. Next, we have forget outdated information. When data becomes irrelevant or incorrect, memory can be cleared to maintain accuracy. Then we have updating of facts dynamically. Agents revise their memory in real time as new data comes in, ensuring their knowledge remains current. Developers use tools such as save memory update memory, and delete memory to implement these functionalities. This level of customization ensures agents are adaptive, efficient, and reliable in long-term application. Let us see what are the step-by-step agent with memories. Creating an agent with memory in Letta is a structured process that ensures the agent can effectively store, update, and retrieve information. Here's a step-by-step approach. The first being defining a system prompt. Shape the agent's personality and objectives by clearly starting its goal and behavior. Second is to create or import memory tools. Equip the agents with tools like save memory or retrieve memory to handle memory operations. Third, we have add memory savings logic, which is customizing how and when the agent should save or update memory based on interaction. Fourth being to interact and validate the memory behavior. We have test agents in various scenarios to ensure its memory operates as intended. Fifth one, we have deploy or iterate on improvements. Once validated, deploy the agent or refine its memory capabilities further based on user feedback. This systematic approach ensures agents with memory are both reliable and adaptable, ready to handle dynamic real-world tasks. Let us see some of the tools used for memory management. Memory management in Letta relies on specialized tools designed to handle data efficiently and adaptively. Here's how each tool functions. Firstly, we have core memory save. This stores active memory used for immediate short-term tasks. Second, we have archival memory, which moves information to long-term storage, preserving critical data for further retrieval. Third, we have retrieve memory, which brings previously stored data into active conversation context when needed. Fourth, we have delete memory, which removes outdated or irrelevant information, keeping the agent's memory clean and focused. These tools give developers full control over how agent remembers, updates, and forget information, ensuring efficient performance across a variety of tasks. Let's see core versus archival memory in Letta. Letta agents uses two-tier memory systems that mirrors human-like recall. Each type of memory serves a specific function. So coming to core memory, functions as short-term memory for live interaction and active tasks. It is also small and fast, frequently updated to handle immediate queries or dynamic situations. And then it is also cleared or replaced often to stay efficient. Whereas coming to archival in Letta, it acts as a long-term memory, sorting important facts, histories, and user performances. Large or slower accessible only when required during the conversation or task execution. Persistent unless specially deleted, ensuring continuity across the sessions. This balance between core and archival memory allows Letta agents to perform real-time tasks while maintaining long-term reliability and personalization. Let us see what is Agentic RAG. So what is Agentic RAG? Agentic RAG is Agentic Retrieval Augmented Generation, which is RAG, takes the basic principle of RAG and enhances them with reasoning and planning capabilities. Unlike traditional RAG system that simply fetch relevant data, Agentic RAG enables agents to plan, reason, and integrate. Whereas in plan, they determine what data to retrieve and why based on task at hand. And in reason, they analyze retrieve information to make informed decisions. Thirdly, to integrate tools and memory, they use external tools and stored memory to process complex queries. This advanced approach allows agents to perform tasks autonomously, scaling efficiently for real-world applications that require both intelligence and adaptability. Why is this importance of RAG for scalable agents? So RAG is crucial for creating scalable, intelligent agents, and here's why. Firstly, handling complex tasks. RAG enables agents to manage large and dynamic tasks by offloading knowledge retrieval, ensuring efficiency without overwhelming memory. Secondly, we have real-time knowledge access. By retrieving up-to-date information from external source, RAG reduces reliances on fixing training data, allowing agents to stay current in rapidly changing environments. Third, we have overcoming context window limits, which is RAG extends an agent's capability beyond limited context window, enabling them to process integrated vast amount of data efficiently. With RAG, agents become smarter, faster, and better equipped to take real-world challenges while maintaining accuracy and relevance. What is the role of external memory in LLMs? External memory is a game changer for LLMs, acting like a person database that extends their capabilities beyond the limitation of context window. And here's why it matters. Firstly, we have functionality. External memory stores facts, documents, and interaction, enabling agents to access information beyond their immediate context. Coming to capabilities, it enhances long-term recall, personalization, and dynamic learning, making agents more adaptable and context-aware. Thirdly, we have efficiency. Similar to how humans use nodes, external memory ensures the agent retrieves only what is needed, reducing the need to hold vast data in active memory. This approach allows LLMs to operate more effectively in complex real-world scenarios requiring both precision and adaptability. How can we implement Agentic RAG with Letta? So implementation of Agentic Retrieval Augmented Generation, which is RAG in Letta, involves a structured three-step process. First one, including setup. Configure inbuilt memory tools such as retrieve memory to manage data effectively. It also integrates external document stores to ensure scalability and seamless data access. Next, we have queries, which defines what data agent needs to fetch and when queries should be triggered. Customization tools to streamlining query handling, making an agent more dynamic and efficient is also part of this query. And lastly, we have results. To process the retrieval data to actionable reasoning steps, use the information to generate intelligent, context-aware responses that meet the user's need. This workflow combines Letta's robust memory management capabilities with real-time data retrieval, enabling agents to reason autonomous and perform complex tasks with precision. Let's see what multi-agent orchestration is. So multi-agent orchestration involves coordinating multiple agents to work collaboratively on a complex task. This approach enables seamless execution and distribution of intelligence, ensuring efficiency and scalability. So some of the key benefits here if you use multi-agent orchestration is enhanced scalability, which is distributing workloads across agents makes it easier to track larger tasks. Second, being distributed intelligence, which is agents specialize in specific functions such as data retrieval, reasoning, or user interaction, creating a modular and efficient system. Thirdly, we have flexibility and modularity. Agents can be updated or replaced independently, making the systems adaptable to evolving needs. What are some of the applications here used is we have data retrieval from vast database, collaborative reasoning for problem solving, and also complex workflow involving task delegation and coordination. Multi-agent system redefine the possibility of intelligent orchestration, delivering solutions that are smarter and faster. Let us see how agents as services work. Agents as services involves multiple agents working together, each providing specific functionalities to accomplish tasks efficiently. This modular approach ensures flexibility and ease of development. And some of the key features includes modularity, which is each agent handle a specialized role such as data retrieval, reasoning, or user interaction. Then we have ease of update, which is individual agents can be updated or replaced without disturbing the entire system. Even also including scalable development, agent can also develop across various platforms and systems, enabling seamless interaction. And some of the benefits includes efficiency. Modular design enhances task execution by delegating responsibilities to specialized agents. And also in troubleshooting, isolating specific agents make identifying and resolving issues simpler. This architecture allows developers to build dynamic, robust systems tailored to complex real-world applications. Now let's see what is cross-agent communication. Cross-agent communication enables agents to work collaboratively by sharing insights and coordinating tasks in real time. This capability is achieved through standardized protocols and message passing systems such as API or shared queries. Some of the key benefits include improved efficiency, which is agents can quickly exchange relevant data, reducing delays and optimizing workflows. Secondly, we have streamlined collaboration. Tasks are divided and delegated effectively among agents, ensuring smooth execution. And third include enhanced coordination, which is by synchronizing their action, agents avoid conflicts and redundancy, boosting overall system reliability. Cross-agent communication is a backbone of multi-agent system, ensuring the individual agents operate cohesively to achieve shared goals. Next, we have shared memory blocks. Shared memory blocks acts as a central data repository accessible to multiple agents within the system. They enable effective collaboration and streamline task execution by facilitating data persistence, which is ensuring critical information remains available for all agents throughout the task lifecycle. And second, we have enabling real-time updates, which is allowing agents to update, retrieve shared information in real time to maintain synchronization and avoid conflicts. Thirdly, being preventing redundancy by storing data centrally. Shared memory blocks eliminate the need for duplicating information across agents, improving systems efficiency. This capability is particularly valuable in multi-agent orchestration, where coordination and communication are essential for managing complex collaborative tasks. Let's see some implementation of multi-agent orchestration. Implementation of multi-agent orchestration involves a step-by-step framework that ensures a seamless collaboration and task execution among multiple agents. First step is design the framework. Here we have to define agents' role and specific interaction, and also assign tasks such as data retrieval, reasoning, and response generation to specialized agents. Second, we have set up communication challenge, which is to ensure seamless information exchange through APIs or messaging systems, which also include establishing standard protocols to enable smooth cross-agent communication. Step 3 includes integrate shared memory, which is to create central data stores accessible to all agents, and this shared memory ensures updates, retrievals, and synchronization across agents, enabling cohesive workflows. And the last step is testing and scaling, which is to validate the framework's functionality by testing it on real-world scenarios. Scale system to handle complex tasks and larger dataset for optimization, performance, and reliability. By following these steps, developers can unlock full potential of multi-agent orchestration, creating intelligent systems that are scalable, efficient, and capable of tackling complex challenges. Now let's see a program for this. So that was all about LLMs as an operating system. Congratulations on completing the LLMs as operating system course by Simplilearn. Now you can experiment on creating different types of chatbots. Thank you.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.